Now we'll go over question 4b. In this question, we calculate some IOs with query optimization. Um, so in this question, we have three tables. We have the pages and the records per page. We're given a few indices, and we have some stats on the columns of the table. Okay, and we were given that we want to execute the same query that we executed in part A. And so the first question is asking us, how many IOs would a full scan of T1 take? So the number of IOs that a full scan always takes is the number of it has to read through all the pages. And so we see that T1 has 100 pages, so the number of IOs that a full scan of T1 takes is just 100 IOs. Okay, the second question is asking us how many IOs would an index scan of T1 take on the index T1.x? Well, let's see, T1.x. Well, it has a height 2, so we would have to read down the 2 index pages. And then we would have to read the 120 leaf pages. So we read the 2 inner nodes and the 120 leaf pages. Note that we don't read any data pages because it's an alternative 1 index. So 122 IOs. Okay, using the index on T2.y, how many IOs would it take to perform an index scan on T2 such that it only returns tuples which match the condition T2.y is greater than or equal to 20? So we start by calculating the selectivity, essentially the number of leaf nodes that need to be read. So the selectivity of T2.y is greater than or equal to 20 is 0.8. Since T2.y has a minimum of 0 and a maximum of 100. We see that the index is of height 3. And so there's essentially 3 IOs to read down to a leaf page. We also have 40 leaf nodes because our selectivity multiplied by the number of leaf nodes is 40. Essentially what we're doing here is we're reading down to the leaf node, and then we're scanning all the way right to the end. So we're not reading down the index nodes multiple times. Then for each of those leaf nodes, we find the corresponding record and we output that record. So how many records do we have in total? We have 200 times 50 for T2. So we have 200 times 50 times the selectivity, 0.8, is equal to 8,000 records. And so the total number of IOs that we do is 3 to read down for the index nodes, 40 leaf nodes that we're reading, and then 8,000 matching records, IOs for each of those. So 8,043 IOs. Okay, the next question. Assume that in the first pass of the Salinger optimizer, the T2 and T3 were both accessed with a full scan and directly streamed into the second pass. So how many IOs would T3, BNLJ, T2 take? Including the cost of the first pass. So that's including the cost of reading T2 and T3 with a full scan. Remember that the number of buffer pages B is equal to 12. Okay, so for this question, we need to calculate the cost of reading in or doing a full scan on T3. And then we can apply the BNLJ formula directly. So T3 divided by B minus 2 times T2. And T3's value is 150, so we have 150 pages in T3. We're doing 150 divided by 10 times 200. There are 200 pages in T2, which gives us a total of 3,150 IOs. Okay, the next question is saying, now we're doing some filtering on T2. So now assume that the full scan on T2 is filtered with T2.y is greater than or equal to 20, and then materialized before the same T3 BNLJ T2 join. How many IOs would this take? And so now we're doing something very similar to before, but instead we're doing materialization. So we need to calculate the IOs of reading in T2, materializing it, and writing it out. So the selectivity of T2.y is greater than or equal to 20 is equal to 0.8. So T2 read of the entire T2 plus the cost of materializing T2 is 200 plus 0.8 times 200. And then our formula is very similar to before, except now we're reading a smaller version of T2. So now we're reading 0.8 times T2 because our T2 was reduced in size and materialized. So now we have a total of 2910 IOs. Okay, so in this next question, we're given the query plan again, and we're saying which of the following query plans will be returned by the second pass of the Salinger algorithm, given the total estimated IO cost and output order. Okay, so recall what we want is we want interesting orders to persist, and we want the lowest cost join to persist, but we don't want to consider cross joins. So in this case, non-cross joins are T1 and T2 getting joined together, and T2 and T3 getting joined together. And for those, we want to consider the lowest cost join and interesting orders. Okay, so what is the lowest cost join between T1 and T2? If you look through everything, you'll notice that that's B. T2, B and LJ T1, the IO cost of 2000. If you look for the lowest cost join of T2 and T3, you'll notice that that is this. T3 BNLJ T2 with the IO cost of 2500. And the only interesting order that we have is on T2.y because it's used downstream in order by and in the where. So the interesting order that comes up is from part I, T2, SMJ, T3, even though the IO cost is greater than H. So these are the only three things that are persisted. Okay, the next question is saying, consider the following modification to the Salinger optimizer. After we determine our final query plan, we tested materializing the output of each operator. Before inputting it to the next operator, we'll reduce the IO cost. And each operator is considered either a single access or a join. So for the query above, how many query plans would we have to consider after the final step of the Salinger optimizer? Okay, so how many single accesses do we have and how many joins do we have? Well, we have the single access for T1, for T2, and T3. And the joins that we're considering are T1 and T2, and T2 and T3. So we have a total of 5 operators that we're considering. And so for each of those, we want to test if materializing is going to help or not help. And so the way we get to our answer is we check 2 to the power of the number of operators that we have. So there's a total of 32 combinations that we can try out. 2 to the power 5. Okay, for the final question, true or false, pushing down on the fly selections in a single axis scan in single axis scans will always reduce the final IO cost of the query plan outputted by the Salinger optimization. Well, in the previous example, we saw that this was true, but is this always true? So what would happen if the on-the-fly selection didn't actually reduce the size by anything? So it just selected everything. In this case, we would there wouldn't be any reduction in the final IO cost, and so the answer is false.